So yeah, I'll just start with a quick intro. Some of you might know me from my work on spaCy, which is an open source library for NLP and Python. So basically, if you're working with lots of text and want to analyze it, spaCy is a very popular package for that. And yeah, I've been working on spaCy pretty much since it was first released. And eventually, my co-founder and I, we started our own small company around it, which is called Explosion. We initially bootstrapped the company with a bit of consulting, but have since been very lucky to focus entirely on developer tools for machine learning and NLP. And our first commercial tool was Prodigy, which was released in 2017. And it's basically a tool for data scientists that helps run more experiments, collect data, label your data, and basically iterate on that whole training and dataset creation process faster. And so that's kind of where we're at now. And currently we're working on an extension product for Prodigy, which is more of a software as a service-y type platform, which helps teams scale up their annotation efforts, have like larger annotation teams, run experiments at a larger scale. So that's very, very close to the first release. And in the future, we're also planning more like an online store for pre-trained models for different languages, different domains. So that's kind of what we're working on. And having such a large community use our software in all kinds of different industries and fields has given us some insights into how do people do NLP and also what's working, what's not working, how to structure your projects. And today I want to talk a bit about like how you can actually make use of some of these hot new topics that were like really big, especially last year, all the cool new achievements in NLP, and how basically a very modern 2019 data science NLP workflow could look like in practice. And so to kind of illustrate that, here's a fictional project. So imagine you're a data scientist, you work at a company, and you have a client who's an international corporation that produce fizzy drinks, and their product is called Cola, and what they want to know is how do people talk about our brand on social media, or in general, what do people think of us, and especially how positive are we perceived. And so someone else on your team has already scraped social media, given like some hashtags and keywords. So you have like about 5 million scraped social media posts to work with. And so you're like, okay, this sounds like a pretty doable project. I think we can do this with machine learning. So you're like, okay, one approach would be let's try and train a text classifier and try to predict whether a post is positive or not. Sounds pretty straightforward. So that's your plan, and so you start mapping out your project board of all the different things you have to keep in mind and all of the things your project is going to consist of. So it kind of looks like that, probably in practice a bit more like that. And that's what's going to take up your time. So you've planned this, and now you're going to start looking at those individual components. So you need to label data, you need to implement your model, you need to train your model, and eventually you need to deploy it somehow so that your company or your client can use it. And usually, if you've ever trained like machine learning models before, you might be familiar with that sort of workflow or that sort of project flow. Here's a very non-scientific graph. We map on that axis, we're mapping the effort, which is basically how much time you spend, but also the size of your training data, how much work you put in, and how much you experiment, how much you do. And on the other axis, we have the effectiveness, which kind of includes your model accuracy, but also how useful your model is. Because you can have great accuracy. If your model doesn't actually do what it's supposed to do, it's kind of useless. So that's like also how happy you are with the results. And the first section, I'm calling this the swamp of uncertainty, because nothing really happens. Like that's the part where we barely see any movement, nothing changes. You put in all the work and you kind of get nothing in return, and you're just waiting for something to happen. Next, hopefully you'll get to what I'm calling the hill of hope. That's kind of the fun part. Accuracy is going up, things are changing. You're like, yay, I'm going to solve my problem, great. And then at the end of it, you get to this, eventually you'll always get to this plateau of frustration. Ideally, that happens when you're already quite happy with the result. But sometimes, of course, it can also just happen at some point. Nothing's happening anymore, and you have to rethink your strategy. So this is sort of like the ideal curve of an ideal project, but of course, in a lot of cases, it can also easily look like that. Probably most of your projects will look like that, because that's just how it is. Data science mostly does not work, and you're trying to find the things that do work. But what you can see here is like the swamp of uncertainty kind of looks the same. You're getting about the same signal from here. It's just like you keep going and going and going, and nothing happens. So that's what I'm calling the quicksand of sunk costs. So the idea here is, well, you keep going. It's sort of like the sunk cost fallacy. You've already put $50 in that slot machine, and you're just about to win, so you might as well put another 50 in there, because otherwise, you lost $50, and that's bad. So like, at some point you need to stop, and you need to know when to stop. And the question here is like, why do we even have all of this uncertainty at the beginning? Like, why can't we just like see results faster? And one reason for that is that, well, the problem is we're not actually immediately solving the problem we're trying to solve. Like, for example, predicting the positivity score. What we're actually doing is we're kind of getting the model in the right state, and we're teaching it a lot about more general things, like knowledge about the language and knowledge about the world. That's what it needs to know first, then we can actually move on to our problem. And that also, that's kind of a very fundamental problem in NLP, and it really comes down to this idea that like language is more than just words. Like there's a lot more going on, there's a lot more context, and we kind of, it really sucks that we always have to start from scratch whenever we're training a model, and we need to teach it all about language and all about the words. And it's like, because for human, it's not like that. Like if I want to follow, a talk on Kubernetes in Polish, sure, I first have to learn Polish. That's like a big step, but after that, I can learn about more things in Polish. And then next time I go to a talk, I can start right there. I already know Polish, and I can like keep going. The model mostly starts at 0 for every task. You can have it a bit, you can give it a bit, more general things to work with, but like ultimately, this sort of knowledge that we really have about the context, in the past, we've really struggled to pre-train that in a way that generalizes well. But but this is changing, and we can see here are some examples to go back to our Cola example. So we have two social media posts here that when you read them, you get what it means. But like there's a lot of very hidden context there. Even the first one, something else. You have to know what this refers to. You have to know that this is a saying. Here you have to know. Okay, you have to be able to pass that emoji. Maybe you know that it's like a reference to a song lyric. Maybe you don't, but like a model will really struggle with that. So the idea is, how can we really make the model learn the meanings of words in context, or even whole sentences? And that leads us back to all of this exciting new NLP stuff that you've probably heard about. So we've, last year we had the release of BERT from Google. We've had Elmo from LNAI. We've had ULMFit from Jeremy Howard and Sebastian Ruder. And Sebastian also called it NLP's ImageNet moment. And it was even picked up by some more mainstream media. And they even, it's not very deep, but like kind of the gist of it, they're getting it, which is the idea is what we're doing here, what works so well is we're trying to predict the next word. That's how, that lets us learn and pre-train the meaning of words in context by basically predicting the next word given its context. And that's proven to work very well. And the nice thing here is we can do this purely based on raw text. We don't need to label it or tell it anything. We can actually feed it a lot of raw text, and we can learn a lot about the language just by making the task, let's predict the next word. And so, of course, when we saw this news, we were like super excited, and we're like, great, finally this works. We've been waiting for this for a long time, and of course we want to make this available in spaCy so that people can use it. But the thing with spaCy is, well, our main mission has always been to provide like fast and production-ready implementations. So, and we also have set ourselves like pretty high targets to make our software actually, usable, which is often a bit different from research code. So, for example, we're targeting 10,000 words per second, which is very fast. Like a lot of other implementations run, can easily run quite slow, which is fine. But like in production, you can't really work with even 1,000 words per second or 100 words per second. That's like at scale, that's way too slow. And we also want our models to be small and cheap to run, which means they need to run on CPU. We don't want, our users don't need like several powerful GPUs just to like predict stuff. That's not really feasible. So we basically ended up with our own implementation, which we're calling language modeling with approximate outputs, also LMAO short. And the idea here is that instead of actually predicting the words, which is more expensive because we always have to keep track of like the actual word text, we are training the CNN to predict the vector of the word given the context. So which is, of course, it's more of a rough meaning representation. It's not as precise, but it still works just as well, and it's much easier, it's much smaller, and we can take advantage of word vectors that we already have. For example, using an algorithm like word2vec or a library like GenSim, it's like actually pretty easy. Take your raw text, train word vectors, and then we're predicting the vector of the next word instead of the actual word. And the great news was also that while we were kind of testing this implementation, had this idea, there was actually another paper released, so I put the reference here, if you're interested. And they ran all these experiments, and they did those experiments so much better than like we could have done, and basically also showed that like, yeah, it works. So this was like really amazing timing, and we're like, yeah, okay, it works. And so the nice thing is also, just to give you a quick overview how this looks in practice, everything I'm talking about in terms of pre-training is actually something you can already do when you install spaCy. You can download some pre-trained word vectors, for example, glove vectors that we ship as a package. And then you can use the pre-train command, which takes raw text, the vectors that we want to use for prediction, and then an output directory where we put those pre-trained weights. And text looks like that. Here we just have like some Reddit comments in JSON-L. JSON-L is like a really great format. If you're still storing your data in JSON, maybe consider using JSON-L because it's really cool. You get all the benefits of JSON, but you can read it in line by line. So here we just have a bunch of raw text, nothing labeled, just really straightforward. And then when we train our model, we can actually pass that file, this artifact that we just pre-trained in, save out the model, and we can immediately use it to predict things. So we can load it in Python, in spaCy, and do stuff with our trained model. And to just give you some accuracy, just some numbers here. This is on a corpus where we're predicting syntactic dependencies. So basically, how words are related, subject, object, and more complex stuff. And normal case, okay, 79 is not bad in terms of accuracy. Then just with the pre-trained word vectors, we already get a nice improvement. With our LMAO pre-training, we get a nice improvement as well, about the same. But the good news is that both of these stack. So together we get like over 3% improvement in accuracy, which is pretty good. Also on like, on kind of the same task, just by stacking up those two things trained on raw text. And to put these into, in context, here are some numbers that Stanford reported on like the same task. So it's definitely, it's definitely pretty good, especially considering that model artifact we trained there is only 3 megabytes. So that's very, very small, and it's also very fast. So, okay, so we have, our little board here again, and we'll just be adding the pre-training because that's definitely something we want to be doing, because that also allows us not only to get better results overall, but get the results faster and need fewer examples. So hopefully, this will kind of help our curve go up quicker, so we basically getting there sooner, and we know whether it's worth pursuing that or whether we should stop and try something else. And so the next thing we can look at is the annotation up there. So still, we're like, well, positive, labeling whether something is positive or not sounds like a pretty easy task. So maybe you put it on Mechanical Turk, a few thousand examples, get them back, train your model, and maybe you start seeing that actually there are a lot of kind of inconsistencies in the data, which is a bit weird. Your model isn't really learning, and so you're like, okay, what's going on here? It wasn't like a particularly difficult labeling task, but the problem is there's like, you look at the data and there's just a lot that like you sort of didn't expect that ended up in your training data, that ended up in the data you scraped, and that maybe you want to deal with differently. So you go back to the drawing board and make some notes here of maybe what we could try to handle these examples better. So for example here, all of this spam and scam stuff isn't very it's usually not very subtle. So we can predict that as well. We can predict, we can train a model to predict whether something is noise, spam, random stuff, or whether it's actually something we're interested in, like a genuine mention of our brand. Same here, what do we do with emoji? Are we leaving them in? Are we sure, do we have enough examples? Are we replacing them maybe with text to give the model a better hint? Because as far as the model is concerned, that's just a Unicode character. Can we handle that? Can we not handle that? And then we get stuff like that where suddenly, okay, the whole process of tokenization, so splitting the text into words is completely messed up because our model is expecting to see at least something that resembles a sentence, and then we get that. And none of the punctuation that's used in there is actually punctuation, so we can completely fail on that, and it's like very confusing. And we're also seeing like, well, normally we would have discarded these things, but they are mentions of the brand, and maybe they're positive. Like, maybe we do want to capture memes, or we want to capture what people say about our brand, because it might not be positive, but like it's interesting information we don't want to discard. So maybe we want to actually add another category to our label scheme in order to reflect that. So this shows that even something that sounds very, very simple at like face value can actually be more complex once you start doing the labeling. And this is still a very easy kind of task, and it just gets more and more complicated once you're actually working on more sophisticated problems, like medical domain, legal domain. There's like a lot there. So that really, we've been seeing this kind of stuff a lot, also in a lot of use cases in NLP, and we always thought actually a good solution for that would be to have the data scientist much more involved in that labeling process initially before you scale it up. You don't want to scale something up that's like bad, and creating the label scheme is actually much more, just as important as like doing the actual labeling. So basically, and that's kind of a workflow we're trying to reflect in our tool, Prodigy. It's fully scriptable in Python, runs on your own hardware. So often if you're working with like sensitive texts, you have the full data privacy because you basically, your examples never leave your servers. You can write Python functions to like ingest your data and play with it. And another thing, we can really implement workflows where we automate as much as possible. We don't want to waste a human's time on doing the same repetitive task all over again. We can use something like active learning where we put the model in a loop. We correct what the model predicts. We focus on the things that maybe are more important to get right, rather than stuff where the model is super confident that it's a positive mention. And we can really, because it's so fast, we can actually iterate much faster. We can label more. We can label ourselves. We can get a feeling for our data quicker. And that's kind of the workflow that we found to work very well. Here are some examples of how this could look. You focus on one thing at a time. You have, either you label something by hand, you have the model suggest something, and then you can give a decision. If you can break it down into binary decisions, that's always great because it means you can compare decisions more easily. If you have 5 people labeling the same thing and you have a binary yes or no answer, it's very, very easy to just say, okay, how many people agree, how many people don't agree, which gets much, much harder if you ask people to type something in. You can have images, we can have more of a multiple choice thing. These are just some interfaces you can kind of put together, and that also ideally, allow you to label a few hundred examples yourself, at least initially, while you're still designing the label scheme, to really make sure that what you have in mind works. Then you can go back, train a model, see what it does, and then once you're like, okay, this is a great plan, we can scale that up and get more people on it. And so here's our little curve again. So I've added another blue one, which basically shows a workflow where you're using pre-training, which means you need fewer examples, higher accuracy, and also kind of an active learning workflow where you put the model in the loop to help you select better examples, automate as much as possible, so you can really collect more relevant annotations faster. And as we can see here, the swamp of uncertainty, finally, we're seeing like results faster. So you can actually, you need to put in less work to see whether it's working or not. Similarly, okay, Hill of Hope looks kind of similar, but even here, the plateau, there's still some uptick there. You can see, okay, maybe if I put in a bit more work, a bit more is going to happen. So both of these combined actually let you, avoid the, the sunk cost. How did I call that? The swamp? No. I forgot my own metaphor. But anyways, you don't want to, you want to know when to stop and how to start going, or when to keep going, and that can kind of help you with that. So together with the pre-training, we'll also add like the active learning here, some example selection. Doesn't have to be super fancy, but like, the less you have to kind of do manually, the better and the faster. And then okay, we're looking at that, and turns out we kind of forgot one pretty important point, which is the maintenance. You've trained your model, you've deployed it, it all works, but it will at some point, go out of date. And the reason for that is that, well, language is evolving. Language changes, and which means your runtime inputs are going to change over time. So these two examples, here's one, 2018 on Twitter versus 2006 on MySpace. That's how, it's very, very subtle. That's how people type, but you already see, it's like, you need all that context. Even, there might be a lot of people who even, just based on those words are like confused by this. But that's how, that's the sort of runtime inputs you just have to deal with somehow. And so it means that, if your model was trained on a lot of stuff you scraped off MySpace in like the 2000s, it'll probably struggle with like today's Twitter language. So the annotation efforts and all the work you put into that shouldn't it shouldn't be a one-time effort where you're like, cool, let's get this done, outsource that, got the data back, trained our model, shipped. You always end up with annotation as an ongoing process to keep your model up to date, and also to kind of capture the changing entities and the changing kind of landscapes and what people talk about. Like one example I remember from spaCy is like somebody complained that like, oh, spaCy's pre-trained model really fails to recognize Bernie, as in Bernie Sanders, in kind of news texts. And part of the reason for that is that the data is very recent, the corpus it was trained on, but it's still old enough that like barely anyone talked about Bernie so much in the mainstream international media. And it is kind of a weird word, or like a weird name. It's very, very unusual to refer to a politician like that. So the model even fails to generalize because it's like weird. It doesn't look like a person. Maybe it's an organization. It's more like an organization name. But even those kind of changes you want to be capturing. So you always want to keep, keep improving the model and keep running experiments. And so one idea here that we've built for that is Prodigy Scale, which basically takes this Prodigy labeling philosophy to the next level. So you can actually monitor the quality and also the progress over time. You can group your experiments and tasks into larger projects. And you can also invite your users, have like domain experts in there, and really structure your tasks in a way that makes it as easy as possible to get like the very valuable knowledge from a human, because ultimately, humans have limited time, especially humans with a lot of knowledge, like a surgeon. You don't want to bore a surgeon with like too much stupid click and drag stuff. You want them to really give you the knowledge that like you don't have, so you can train your model. And you can label just the same way with a variety of interfaces, and kind of have that whole ongoing thing integrated into your workflow. So every month you can ship a new updated model that captures what's going on, and you can run your training experiments, and you can see, is my model improving? Is it not improving? And ultimately, the goal is you want kind of a workflow like this. Because most of your projects are likely going to fail. That's just how it is in data science. Like, 90% just fails, but 10% succeeds. And out of that, there are really some things that like succeed wildly and are like, can potentially, save your whole company and like really, be kind of a, the turning point for your project. And that also means that like, you want to find those, and you want to stop doing things that like don't work as early as possible, and keep doing the things that do work, and then ideally, end up with the best possible solution without wasting too much time and effort. And so here, in summary, here's sort of the kind of final workflow with the new components that you can use. Transfer learning, pre-training, the idea of, okay, you're enriching the model with general knowledge about the world, so you get better results faster. You improve the way you're labeling data and encoding the really specific problem that you want to solve. And you make sure your model stays up to date and you don't end up with this outdated artifact. And so, you still have to accept failure. None of this is like a magic recipe. You still have to do the work. Nothing, it's not, NLP is still very, very difficult. A lot of it comes down to making the right decisions, and making the right decisions is hard. But hopefully, with all the new tools we have, I think we're really on a good track to be much better at solving NLP problems and coming up with like best practices and workflows. Thanks. Cool.